LUMO type, the unfilled energy band that we are familiar with, and valence band are this filled HOMO type state that we are familiar with in MO theory. Okay, so these are sort of loosely unfilled state, and these are filled state in your solid, and so you this concentration so you are starting with silicon. You can start with one material and just add impurities to the silicon, and you can create p-type or n-type silicon by changing, basically inducing a little bit of impurity into it with the appropriate amount of impurity to create extra whole state or extra electrons into it. Okay. So so things like boron will create, for example, boron will create p-type, and nitrogen, for example, or phosphorus will create n-type, something that has more electrons than silicon. Okay, so that's how you create this, and if you put them, create a junction together. So in the case of solar cell, effectively is a p-n junction, and in this p-n junction here, there's an interface layer. So sometimes you see this jargon if you attend a solar cell talk. They would call it PIN junction, and I is sort of the extra interface region. Effectively, it is just PN junction, but in this fuzzy region, they like to emphasize that's where the photon absorption occurs. So the light comes in, the sunlight comes in, energize photon absorption in the interface region, and then you create separation of electron hole pair occur in the interface region, and you try to store the electron. Okay, so that's the jargon as you read the literature when you see a PIN junction. That's what they mean. It's effectively, technically, just PN junction and the interface where the action takes place. And why is this interface so interesting? It's because, you know, if you have PN junction, you have an imbalance of charge, and you create effectively a potential barrier between these two. Okay, so from the strict electronic point of view, once you got a potential barrier, what does it mean? It means that you can by applying a bias, right? So if you apply some voltage potential between these things, you could lower this barrier, right? Effectively, you can lower or raise the barrier depending on which way you apply the voltage. So what does that mean? It means that you create a gate, what the electronic engineering call a gate. So by manipulating this voltage, you can either pass electron or you don't pass electron. Okay, and when you have something that either 0 or 1, no electron passing or electron passing, what do you have? You create digital logic, right? Binary logic. So that's why it's such a big deal in the electronic world, because by using a PN junction, you create a diode, in effect a diode which only effectively allow electrons to go through in one direction, effectively in one direction, and then you can create digital logic, binary logic, 0 and 1 type logic. So here's a effect of this so-called rectifying effect, whereby if you forward bias your diode, your PN junction, which is your diode itself, you would have current going in this way. Okay, going in this way. But if you try to reverse bias, so the voltage you need for passing current is very low in this direction, whereas the voltage you need for passing current in the reverse direction is extremely high. In other words, you will stop, right? The current will not pass because you need so much more voltage in order to lead to passage in the reverse direction. Okay, so you have in effect, you created a diode, and the diode leads to digital electronic, binary electronic as we know it today, so-called classical computing because you now have 0 and 1 logic by just manipulating these p-n junctions. Now the next thing is that instead of putting two semiconductors together, P and N together, you can just put a semiconductor and a metal together. Okay, if you put a semiconductor and metal together, just in contact, in physical contact, what do you have? You created a metal semiconductor interface. Okay, so that's another interesting thing. And the semiconductor, metal semiconductor interface is what is known as the Schottky barrier, and how the Schottky barrier, a very famous name, because everybody heard about this Schottky barrier. And what happened is here is between and again you would have some sort of a barrier effect. So you have metal, right, which you have all the electrons are filled to the rim, right, because there's no conduction band, so to speak, right, because in the case of metal, you have everything filled down to the lowest possible energy level. And then you have semiconductor, you would have valence band and conduction band like this. And then if you put them together, just put them in physical contact. That's all you need to do. You would have a valence band of the semiconductor like this. The metal, of course, is all filled to the Fermi level, like that. And you have an imbalance in here. And because of this physical contact, you have to reestablish equilibrium, because you cannot create a discontinuity of your band structure. So this becomes a system. So the system cannot allow discontinuity. So what effect you have is, again, you have some sort of bending effect between the metal side and the semiconductor side. Okay, and here you have a N-type semiconductor. So what you got is that you have the negative type, and so you have equilibrium of the Fermi level, right? So this is the Fermi level of the semiconductor, and of course, in the case of metal, the Fermi level is just the top, your metal's electron band, and the Fermi level has to lower, and this has to raise, and then it equilibrium like this. Okay, and then from there, what you got is that you have to reestablish your field band, your valence band, and conduction band like this. And so what in effect happened is it created a barrier, because you see, like, once again, you create a potential barrier between this. So, and this barrier is known as Schottky barrier between the metal and semiconductor itself. And so again, what can you do with this barrier? Well, again, you can create a diode. In fact, you can create a diode. So what you have is here you have a Schottky barrier. So once again, you have semiconductor side, metal side, and you allow it to reach equilibrium, right? Reach equilibrium. So the Fermi level would be at the top, same as the semiconductor, like this here. And so you have this barrier height in here. So if you have extra electron, right? You have extra electron in here. The electron cannot flow out because this basically is trapped, right? Because you have this barrier height, you get trapped. And so what you could do is that you can apply a potential on this metal here. If you apply the potential on this metal, you can either apply a high potential. So in effect, you're changing the barrier, this thing here, the Fermi level, the field electron value, raise it, right? Then no electron can go through because you're making this barrier height even higher. But if you lower, you apply a less or more negative, right? Depending on polarity, you lower the level, right? So then the barrier height becomes smaller, right? Because you apply a different bias to it. Then electron can flow through due to thermal motion. So you have a better chance of flowing through. So this is known as forward bias, which decreases the barrier height, and the reverse bias, which raises the barrier height. So you stop current. This is allow current to go So here again, you have a way to create a dial, and once again, digital electronics. Okay, and last bit of application also related